Okay, we're going to look at electromagnetic induction and look for any violations of relativity. Uh, I hope the guys have uh, the video set up, and if so, we can look at the video before I continue with the slides.
Yep, pulling it up now.
Okay, what we saw in the video was the actual experiment which tests Faraday's law. In this slide called Faraday's anomaly, we're going to see why some of the predictions of Faraday's law are not true. First of all, what is it Faraday's law? The EMF, the voltage produced, which is the generator principle, depends on a charge, Q, moving through a magnetic field, B, with a speed, V, and what we must have is the speed of the uh, uh, conductor, C, relative to the magnet. So Faraday's law originally said you must measure the speed of the relative speed of the copper, the conductor, and the magnet, the iron. What you saw in the experiment was a copper disc, which is the conductor, located directly above an iron disc, which provides the magnetism. A motor provides the capability of spinning either one independently. And up here we have two brushes which pick off the voltage between the inside and outside of the conductor. And as you saw in the video, the wires connect to an oscilloscope, and you saw whether there was voltage produced or not. So I'm going to go through the results, the results of the test for those that are important. The chart shows that there are 8 possibilities for rotating disk, that is the copper, rotating magnet, or the meter rotating. We are only going to consider the meter as stationary. So there's only going to be 4 possibilities. Number 2, line 3, 5, and 6. Those are the ones that we consider where the meter is stationary, the oscilloscope. And in this case, the disk rotates and the magnet is stationary. So Faraday's law would predict that there's relative motion between the two. And over here, we see the voltage is correct as predicted by Faraday's law. On line 3, the disk rotates and the magnet rotates. Now, according to relativity, the two are rotating together. There's no relative motion, so there should be no voltage. But in this column, we see in red, there is a voltage. So line 3 violates Faraday's law if you use relativity. The other ones that we want to check are meter stationary, so that's line 5. The disk is stationary and the magnet is stationary, and that's no relative motion and there is no voltage. That's correct. Disk stationary and magnet rotating, that should produce a voltage, but it doesn't. So this is the second violation of Faraday's law using the law of relativity. What I want to look at next is the summary. When the disk spins, we found that the test agreed with Faraday's law, and so did special relativity. Now, if I use, instead of the relative motion between the conductor and the magnet, I use the motion of the conductor relative to the Earth, the lab frame, that also agrees. When I considered the magnet was spinning and the disk wasn't, then I get no for special relativity, and that doesn't agree with what the experiment shows, which when they both spin, there should be no EMF produced. So there are 2 conditions in which Faraday's law are violated. But if I use, instead of conductor relative to magnet, I use the conductor relative to the laboratory, I do correctly predict the voltage, the generator principle. So SR in electromagnetism is rejected, and the alpha model, meaning one in which there is an absolute lab frame corresponding to which predicts correctly the results that we get. So we see in mechanics and we see in electromagnetism that the lab frame must be used in order to predict correctly using the laws of physics.